So for this lesson, we kind of open up with some different patterns, and we're actually switching into kind of a color theory that we're going to look at how that relates to graph theory. So basically in class, we kind of opened up with some different pictures of patterns, and we looked at what's the fewest number of colors you could use to color in those patterns and kind of make a conjecture about that. So back over 150 years ago, there was a conjecture made that it looked like you could always just use 4 colors or less. But it actually was proven in 1976. So at first people just kind of assumed that that was possible. But in 1976, it was proven. So sometimes we can take those old ideas and discover new techniques and different things in mathematics that can give us a more solved problem. For example, then turning ideas into theorems. So remember that a theorem is when we can have something that's proven to always work. So this states that any pattern or shape can be colored with 4 colors. 5 colors will never be necessary. So when we say coloring with 4 colors, what we're saying is no 2 colors can share a side. So that's what we're looking at here. We're trying to figure out how we can accomplish that. So the best way to do this is to start with 1 color in a section. So you can use colored pencils, or if you don't have any kind of colored pencils or markers around, and the lines don't need to be perfect. Don't spend too long just with coloring. It's more the idea we're trying to get behind. But you can also use your pencil and just mark it with a letter of a color. You could use a P for pink. But from here, we want to kind of look and see what pieces can't be colored the same that's attached to pink. I can't color in any of these 2 shapes pink, but I know this is going to have to be another color. We always start with trying to use the fewest number of colors possible. But now that I've done this one yellow, this third section also has to be a new color. It can't be pink or yellow because I can see that if I drew pink here or yellow here, that they would then be touching and sharing a side. So I'm going to go ahead and switch to a third color here, and then we want to see if it's possible to complete it with just 3 colors. So from here, it is possible to use pink again. I can't use pink on the border because it will touch here, but I could use pink on either of these 2 sections. The only problem we encounter here now is that we have pink, yellow, and green all touching this space here. So we wouldn't be able to use any of those 3 colors. And in fact, we do have to now introduce a 4th color. But we can complete the whole graph with just those 4 colors. Because this outside border, we can choose to color either orange or yellow, and either color would work. We do not need to do a 5th color for the border. Again, I'm just doing this pretty quick because I don't want to waste time with the coloring aspect, but just to kind of give you an idea of those shapes. All right, now looking over to this one, let's start with 1 color here in the center. We can either start in the center, work our way out, or vice versa. The thing that kind of confuses people on this theorem is that when they're looking at a shape like this, for example, and they say, well, this is orange, and I can see this space touches 1, 2, 3, 4, 5 other spaces. Don't I need 5 different colors to continue coloring? But recall that we're trying not to let 2 of the same colors touch. So if I put green here, and this green is okay to touch orange, then this spot can't be green or orange. So let's say we switch to pink right here. But to color in this space, I can use green again because this green will not touch that green. It's okay if orange touches green in 2 different places. Orange just can't touch orange. Green just can't touch green. So then we try to reuse colors as often as we can. But we want to be careful about where we reuse them because we want to be aware of the fact that we still want to try to get it done in less than 3 colors or less than 4 colors. So maybe we could switch back to orange here. And I want to make sure I don't use a 4th different color here. I can see that this piece is touching green, pink, and orange. So I am going to have to resort to a fourth color. So let's say, I won't color in the whole thing exactly, I'll just kind of do a quick little sketch here. So if we throw yellow into this space, we know we can't use yellow here, but we can go back to pink. Green, orange, and yellow, that won't work here, but I can go back to pink. So we're kind of just working our way around so that we can make sure we don't repeat any of those colors again. Now again, we got to be careful here. I can already see green touches, pink touches, and yellow touches here. My only option now is that I need to make sure this can be colored in orange, or whatever colors you're using. Doesn't have to be the same as me. Because I might have resorted to trying to put orange here, but then that would have made it so no colors can go here. So you have to be kind of careful with that sometimes. Now that I've used orange there, here I could use yellow and green. I could put a green here. This is not touching any other greens. But the only color that can go there is yellow again. So I'm going to put the yellow here. If I had put yellow there, then nothing could go here because it's touching all the other colors. So then I can switch back to pink. So it's okay to alternate colors like that. Now, I notice on this one, these two are the ones that most commonly people kind of struggle with figuring out the coloring on those. But let's start with one color in the center here and kind of work our way out. So for the next box, we definitely need a new color. So let's go yellow. Those definitely have to be two different colors. And this third section also has to be different than those two because it does touch pink and yellow. So let's switch to green for that section. Okay. From here, we're going to have to use a fourth color in there. We can see that this pink, yellow, and green all touch this space here. So let's go ahead and switch to orange for that piece and color it around real quick. And then it kind of feels like we need to switch to another color, a fifth color. But remember, we can always avoid a fifth color. So if you look carefully, the yellow is actually not touching this section, even though it's touching pink, green, and orange. So I can switch back to yellow here. Now I can see this piece touches yellow, green, orange. So I've got to switch back to pink here. And then we can kind of decide which colors we want to use from here on out. We are going to have to be aware of the fact that this should be yellow or green, so we don't want to use yellow and green here. Let's go ahead, since it's touching pink and orange, we'll just go ahead and use a yellow here. And then we can go to green. This has to be green because it's touching pink, yellow, and orange, but I can switch back to pink for this section. This area does not touch any pinks. And then for the last bit here, we could switch back to green. So hopefully that kind of gives you some insight onto the process. You just want to work your way around, look at some of the options, but it can take time. It can take time to fill them in. It can take time to distinguish when to use which colors. So if you look at the next page here, we can kind of show you how this process can be simplified a bit. So the way coloring maps is connected to graph theory is what we want to look at next. Instead of coloring in all of these big chunks and looking at where they connect and trying to be careful about how many connections it has, we can take the graph, the map, and turn it into a graph with vertices and edges. So where I have each circle just represents those pieces of, if it's a map, you can think of it as a piece of land, but every different territory is just one little circle now. So now I can just color in each little circle and connect them and see what 4 different colors need to go where. So let's practice on this map of Central America. Turning this map into a planar graph is going to start with Belize here at the top. And what I like to do is just label with the first letter of the country so that we know which ones we've already done and where they should connect. So next we have Guatemala. And those two share a border, so they get a connection right there. Then we can see Guatemala is also connected to Honduras, El Salvador, and El Salvador is connected to Honduras. So when I put Honduras on the map, it's not connected to Belize, but it is connected to Guatemala, and El Salvador is connected to both Guatemala and Honduras. We have another country, Nicaragua, attached to Honduras, and then it looks like the rest of the way down, they only make one connection. So we have a Costa Rica, and we have Panama. So when we create the graphs like this, they don't necessarily have to stay in that same exact shape. What we're more concerned about is which connections it has, so we could use the proper colors. But if it's already in a map form, it just sometimes tends to be easier to draw it out that way. So then from here, that's when we could start to color it in and check to see how many colors it takes. So we won't do that yet because we're going to have plenty of practice with that on the next page when we talk about chromatic numbers. So the chromatic number is the minimum number of colors that will be required to color in any graph, such that no two adjacent vertices or connective vertices have the same color. So for example, and you can't really tell super well on black and white, but this color is the same as this color. So they're not connected. It's okay that it goes here and then goes to there. They just can't have a direct connection from that vertice to the next. And then these two colors are also the same. And that's also okay because they're not connected. However, we do need a third color here because this can't be pink and it also can't be green. So that's what makes this graph have a chromatic number of 3. So that means it can be done with 3 colors. So we want to try to find the least amount of colors necessary for these ones. I can do the first one with you, and then at any point I want you to just pause and go ahead and color those in, and then we can check them together. But I'm going to start the first one with you. Let's say we start on A with 1 color. Then usually you want to switch first to your second color before going back to pink. So on B, I can see B needs to be green. But then see anywhere else you can use that color. I can also use it on F because it's not attached to B. I can't use it for C or E because those are connected to the greens, but D is also okay to be green, not connected. Now switch back to your original color. A and E are not connected directly, so I can make E pink. A and C are not connected, so I can make that pink as well. Meaning I was able to complete the graph with just 2 colors, so it has a chromatic number of 2. So take a moment to pause, and I want you to try these ones and see what chromatic numbers you get. And then when I come back, I'm going to show you what chromatic numbers they have. Okay, if you need a little clue to help you out, these 3 should be able to get done with 3 colors. So pause again and keep working, and then we'll see what colors you end up with. All right, if you're not ready for the big reveal, then go ahead and pause for a little longer, but this is how you can achieve each of those by only using your 3 colors. This one originally looks like it could be done with 2, but you have to be careful of this connection that comes around the outside. So this, I would have to switch back to orange, but orange can't touch orange here. So that is still considered a connection with those 2. So you do have to switch to a 3rd color there. Okay, now for the back, we want to look at sort of applying this to some more real-world scenarios. So what we want to think about is creating a graph kind of like how we did here with the map, where we made circles and abbreviated them by the name of the country. The clubs are represented by the vertices. So we can start with math here. And then what we want to look at is creating a club for a circle for each club. You can start by putting them around in a circle, or you can just do one club at a time. But you want to look at which clubs are connected. So math club has Dana in math and in debate. So math has to be connected to the debate club. And then Dale is in math and science. So we're also going to have math attached to a science club. And then Dale is also in art. So if I have art, then art, science, math, those are all connected. And then also Spanish club. So he's got a lot of clubs going on. So those ones cannot be connected or cannot be held at the same time. And go ahead and try to add in your art and computer also, and see if you can make some more connections, and pause the video. All right, so Dale wasn't in debate or computer, so that will help us to be able to see at least the colors are representing the day of the week. We can see that maybe it's possible to split it into 2 days, but we are going to have an issue with having all of these 4 clubs on the same day. So let's continue here, and we can see that Christy is in math and debate. We already have a connection between math and debate, so we're good there. We don't ever need to have double connections because we just already know they're not going to be the same color. Travis is in debate and computer, so let's add computer club here. In fact, we're also going to need to attach that to math club, so maybe we'll draw it out here. So usually if you can get them kind of in a circle, that'll make it a little easier. So math is connected to computer club by Christy, and Travis is connected from debate to computer club. And then Rachel is our last connection. That's going to be between computer and art. Okay, so from here we need to take a look and see how many colors we can get this done in, and if it'll be possible to schedule it in as few days of the week as possible. So starting with math, we already know that math has a person in at least every other club. So no matter what, math is going to have to be on its own day in order to not have any scheduling conflicts. But then if we host Spanish club on a different day, there is no connection with Spanish and debate, so those 2 clubs could be held on the same day. We also don't have a connection from Spanish to computer, but we do have a connection from computer to debate. So we can't go back to yellow or green anymore because Spanish has a connection to art and science. So we're done with that color. Now let's switch to another one. So we can see that this club can meet, computer club can meet at the same time as our science club, but not the same time as art club. So our art club is going to have to be another separate color. So then when creating the schedule, we are going to need 4 different days. Let's say we do it on a Monday, Tuesday, Wednesday, and Thursday. Most people probably wouldn't want to go to an after-school club on a Friday. So then we would just have to say, okay, math would go on one day, art could go on one day, and then it's okay to have Spanish and debate go together, or computer and science go together. So however you want to create that schedule. But just make sure that you are, for sure, there's no people that have the same Spanish and debate. Nope, Dale, okay. And then just being careful with those connections. So let's try another one down here. This one's going to be 7 different chemicals. So to keep this one a little easier with our graphing and the connections, let's just go ahead and immediately start with 7 circles. 7 circles in a circle. 5, 6, and 7. Creating a circular graph Notice that this one ended up becoming pretty circular as well. Leaving it more open in the middle, it makes it easier so that each number can reach every other number. So what we want to start with here is looking at chemical 1. Chemical 1 cannot be stored with chemicals 2, 5, and 7 in order to be safely stored. So I want to make a connection between 1 and 2 because 1 cannot be stored with 2, so I know they need to be different colors. 1 also cannot be stored with 5, and 1 also cannot be stored with 7. So with these three numbers, 1 should have 3 connections to 2, 5, and 7. So that list is done. Now, as I look here on number 2, 1 and 2 cannot be connected, and I've already taken care of that one. So let's go to the next one. 2 and 3 cannot go together. 2 and 5 cannot be stored together, and 2 and 4. So we should have 1, 2, 3, 4, 1, 2, 3, 4. That one's done. And then for chemical number 3, cannot be stored with 2, already made that connection. Also cannot be stored with 4 or 6. So 3 should have 1, 2, 3 connections. That one's good. And the further we get down the list, the more you'll start to notice the connections have already been drawn. So we have 4 and 3, 4 and 2 are already drawn. So we just need to make this last connection to 4 and 7. On number 5, there should be 4 numbers connected to 5. We already have 2. We already see 5 is connected to 1 and 2. So now we just need 5 to be connected to 6 and to 7. And then check 6. That one should already be done. 5 and 3. 7 should also be done already with 1, 4, and 5. So take a second to pause if you need a little more time to write down your graph, and then we'll go ahead and take some colors to figure out how many different storage facilities would be necessary in order to keep all 7 chemicals. So we don't want to build 7 different storage facilities just to hold one type of chemical. We're trying to build as few buildings as possible to save money, but we want to make sure that they're still safe facilities. So starting with chemical number 1. Chemical 1 cannot be in the same facility as chemical 2. So let's switch colors. And then let's see what else can be stored in the green facility. 7, anything that's not connected to 2. So 7 is good, 6 is good, but nothing else. All of these have a connection to 2. So we got to switch back to pink now. I am able to store number 3 in the same facility as number 1. I can't go pink here because of the connection to 1 or to 4 here. But I can see there's no connection between 4 and 5. So once I get to my third color, they're actually going to be okay to be stored together in one facility. So the different storage facilities that are necessary is we would need 3 different storage facilities. So we could store 1 and 3 together, 2, 7, and 6 can go together, and then 4 and 5 together. So you'll have a practice paper now that you can work on, and you'll have different color theories to look at and different real-world scenarios. Let me know if you have questions.